Hello and welcome back to Introduction to General Relativity. In today's lecture, we're going to continue our discussion of the linearized Einstein field equations and study one of their most striking solutions, namely gravitational radiation. In the previous lecture, we looked at the Newtonian limit of the linearized Einstein field equations. However, in that limit, the gravitational field doesn't really change with time. But in general relativity, the gravitational field is a dynamic entity, and this leads to the possibility of gravitational radiation. Just like there is in electrodynamics, the field is dynamic, or the electromagnetic field, and supports wave-like solutions, so can general relativity. And we can already study this at the linearized level of approximation and determine such gravitational wave solutions. So we need some kind of equations to get started, and we're going to use the source-free equations, source-free linearized equations that we introduced 2 lectures ago. However, we're going to work in this particular gauge that we also introduced in the previous lecture, whereby the divergence of the gamma AB line over line metric is 0. And in this, according to this gauge choice, then the linearized Einstein field equations become this extraordinarily simple set of partial differential equations of second order. So as I just to emphasize what I just said, this first equation here is the gauge fixing choice. Let's say gauge choice. As we'll see, it doesn't completely determine the gauge. So this condition 1 doesn't completely fix the gauge. There's a little bit of freedom left, just like in the Lorentz gauge in electrodynamics. So we are still free to make the following gauge transformation. Namely, we're allowed to take this perturbed metric and make an infinitesimal diffeomorphism generated by the vector field psi A, as long as condition 3 for today, this vector field obeys this equation here. So as long as the vector field obeys this D'Alembert equation here, then equation 3, then there's we could still able to make a little bit more gauge, we still have a little bit more gauge freedom left, and we can exploit that actually to simplify things in a moment. And you'll see that equation 3, or the gauge transformation determined by equation 3, doesn't affect the gauge choice specified by equation 1. So we're going to use this freedom now to make our life a little bit easier in looking for gravitational wave solutions. We're going to introduce the so-called radiation gauge, which will be quite handy in a minute. So the radiation gauge is determined by the following conditions, namely gamma is 0 and gamma naught j component is also 0 for j equals 1, 2, 3, and gamma itself is just the trace of gamma, right? Now it turns out that if the stress energy tensor isn't just 0 in a region, but actually 0 everywhere, then we can achieve a slightly stronger gauge fixing. So if the stress energy tensor is 0 throughout the entire universe, there's no stress energy at whatsoever, then we can further achieve the condition that gamma naught naught is separately 0. So we haven't got to the radiation gauge yet. We have to actually find a vector field psi A that can bring us into this radiation gauge. And the way we find our psi is we simply substitute in this gauge fixing condition here. We simply substitute that in to these equations down here for the radiation gauge, and then we solve. And we have to solve the following equations somewhere. On a fixed initial surface, t is t naught. So you pick some t, some time in the global inertial coordinate system, and you solve these following equations for psi. So here they are. They're just, it's hardly worth calling this an exercise. It really is just the equations for psi determined by substituting the gauge transformation equation into the gauge fixing conditions. It may look a little complicated, but it's nothing more than what I've just said. And also we are further, this is we take the time derivative of the previous equation. So this equation that I'm just writing out here is just the time derivative of the previous equation. However, this becomes extremely important for fixing the radiation gauge throughout time, because if you demand this equation is solved, then the gauge doesn't change. And this final equation is nothing but this third equation where we've taken the time derivative, an additional time derivative. So this is an initial value problem. It gives some initial values for psi mu and their time derivatives, and then we solve them. So it's an initial value problem. So given psi mu on and its time derivatives on the initial time surface, we solve for psi mu throughout space-time. And one then has, which is an exercise, that not only is gamma equal naught and gamma naught j equal naught, but we are on the initial time surface, but throughout space-time. or to be more precise, in the source-free region. Right? The minute you get to a region where there are sources, then this is no longer valid. So if TAB equals 0 everywhere, we can ensure this additional gauge condition 3 that I mentioned earlier, namely that gamma naught naught, sorry, not 3, but I haven't named it actually. So we can achieve gamma naught naught equals 0 everywhere as follows. Namely, we note that gamma equals naught implies that gamma naught b bar equals gamma naught b. That's the first step. And then equation 1 then tells us that the time derivative of gamma naught naught is automatically 0. And then, well, we solve the linearized Einstein's equations. And they tell us that the Laplacian squared of gamma naught naught is minus 16 pi t naught naught naught, which is 0. But that tells us there's only one globally valid solution to that equation, and that is that gamma naught naught is a constant. And we can shift gamma naught naught by that constant. And that doesn't contradict any previous equations. So we can assume further that gamma naught naught is constant only in the case where the entire universe is devoid of matter. Okay, well now I've managed to convince you, I hope, that the radiation gauge where gamma is 0 and gamma naught j equals 0 can be achieved by a very specific judicious choice of diffeomorphism generated by vector field psi. Now let's try and find some waves. And the way we find waves is the way we always find waves. So we assume that the dynamical object that we currently have, namely the perturbation to the metric gamma AB, has the form of some constants multiplied by e to the I times by some wave vector dot product with the position. So we just make a wave ansatz. And we substitute it into the linearized Einstein equations. So that's our assumption, that we have a wave, and then we're going to substitute that into linearized Einstein's equations and hope that we, well, find a wave. So substituting into linearized Einstein equations, which I believe I've labeled 1 today. Well, okay, firstly the gauge condition. So 1 and also 4. Oops, sorry. Let's not get ahead of ourselves. Let's first substitute into 2, which is the linearized Einstein equations. What does that tell us? Well, that tells us that k mu is 0. Okay, so it's null vector. And equations 1 and 4 require the following conditions to be solved. So we've got that equations 1 brings down one factor of k, equation 4 forces h naught nu to be 0, and also the trace condition being vanishing requires that h mu mu is 0. Now we've got a whole bunch of equations here, right? We've got 1 plus 4, so that's 5 equations, plus 4 is 9, plus another one is 10 equations. Yeah? So we have 10 equations that need to be solved in order for this wave-like solution to be a solution. But only 8 equations are actually independent. Because A and B imply that well, A and B together imply that h naught nu k nu is 0. And that should tell us, yeah, together they imply the same equation. So that's why they're not independent. So A and B both imply h naught nu k nu equals 0. So only 8 equations are actually independent of these 10 equations. And now, what have we got to solve for? How many degrees of freedom do we have left? Well, a symmetric tensor of type 2, 0, 2 has how many degrees of freedom? Well, it's a matrix, right, with 4 rows and columns, and it's symmetric, so you only have to worry about the diagonals. They're independent. 4 plus 3 upper diagonal, 7, 9, 10. All the other entries are completely determined. So this has only 10 independent components. So just this naive variable equation count leads us to conclude that there are only 2 linearly independent solutions. For this HAV. So there's only 2 linearly independent wave-like solutions to Einstein's linearized Einstein's field equations of wave-like form. But that's sort of 2 is bigger than 0, and that's a pretty striking prediction of Einstein's theory that the gravitational field itself has dynamical wave-like solutions. And that's a feature that one does not find in the Newtonian theory. It's worth digressing to just talk about lower dimensions. I think this is particularly interesting and highly relevant for investigations into quantum gravity at the current time. Does one have gravitational wave solutions in lower dimensions? Well, we can take a look at 2 plus 1 dimensions. Here, the gauge if you do the count, the gauge conditions imply 6 independent equations. So if you go through and do exactly the same argument what I gave above, you only get 6 independent. You get 6 independent equations. However, a type 0, 2 tensor in 2 plus 1 dimensions has 6 components. So actually, there's no a degrees of freedom count would tell us that the equations can't be or can be solved, but there are no degrees of freedom left over, and therefore one concludes that there's actually no gravitational wave solutions in 2 plus 1 dimensions. Now it's worth pointing out that we could have guessed this already. And the reason is that there's a very interesting little argument you can make that tells you that the curvature tensor is completely determined by the curvature scalar and the Ricci tensor in lower dimensions. So the curvature tensor RABCD in 2 + 1 dimensions is completely determined by the following equation involving the metric, the Ricci tensor, and the Ricci scalar. And so the minute you know the Ricci tensor and the Ricci scalar, well, you know the Riemann curvature tensor, and therefore you know all the curvature information, or the local second order curvature information about your manifold. So in 2 + 1 dimensions, there's actually no more information that the Riemann tensor gives you that you didn't have before with the Riemann, with the Ricci tensor and the scalar. And why is this? Well, this takes us a little bit further away from where we're going in this lecture, but it's worth explaining why. It's a good homework problem to go through this. So this is because you can decompose the Riemann curvature tensor. You can decompose it in terms of RAB, R, and a completely trace-free tensor called the Weil tensor. And then you note that decomposition, the condition for the this decomposition in 2 + 1 dimensions, you note then that this Weil tensor vanishes, and that leads to that equation that I wrote above. Now, how much you can convince yourself of that, we'll just look at the number of independent degrees of freedom of the Riemann tensor and just do a count of the number of independent degrees of freedom, and then you will quickly convince yourself that there's no more information that can be added. All right, that's side remarkers if you're interested in following this up. Now why is it that we could have guessed that there's no gravitational waves in 2 + 1 dimensions? Well, take a look at Einstein's field equations, or look at the vacuum Einstein's field equations. What do they read? Well, they read RABCD minus a half GAB times the Ricci constant is 0. Well, that equation, if you contract that blah blah blah, you quickly conclude that R is 0 and RAB is 0. But take a look at this equation, this condition here we have for the Riemann curvature tensor. That tells us that R is 0, and so is the Ricci scalar. So the whole Riemann curvature tensor vanishes. So the vacuum Einstein's field equations in 2 + 1 dimensions already imply the vanishing of the Riemann curvature tensor. There are no possible waves-like solutions to the Einstein's field equations in 2 + 1 dimensions. Well, before we move on, I should, of course, emphasize something that you've probably, no doubt, already heard, and that is that gravitational waves are far from being a theoretical possibility. They are, in fact, now established, observed physical phenomena. And one of the most dramatic discoveries of modern times was in fact, the detection of gravitational wave radiation emitted from a binary and spiral black hole merger, and they were detected actually in Hanover. Well, the data was analyzed in Hanover, in Germany, in 2015 via laser interferometer. So it's impossible to talk about gravitational radiation without mentioning this most striking and celebrated experimental discovery in 2015. So, in the last part of today's lecture, I want to move on from the topic of solving Einstein's field equations in perturbation theory in a linear order, and I want to move on to discussing full or complete solutions to Einstein's field equations applicable to the entire universe. So we're going to move now to the topic of homogeneous isotropic cosmology. So our goal in the next couple of lectures is to be as bold as possible. We're going to try and extend the domain of applicability of Einstein's field equations to the entire universe. We're going to try and make a model of how we think matter is distributed in the universe, of stress energies distributed in the universe. We're going to make a model of this, and then we're going to try and solve Einstein's field equations. Now, obviously, we can't do it in the complete generality that would describe the entire universe. Instead, we're going to make a couple of extraordinarily massive simplifications, and in particular impose lots of additional symmetries, and in the end we'll end up with a pretty small set of equations that we will be able to solve, and it's those solutions that will occupy us for a large number of lectures. So yeah, as stated, our goal now is to solve Einstein's equations in a case of relevance for the description of our universe, and this is impossible to do for an arbitrary matter distribution. However, what we can do to make progress is to assume a sufficiently homogeneous and isotropic distribution of matter. And so that's the goal now, is so to solve Einstein's field equations, the GAB is 8 pi TAB. We assume a sufficiently, you only assume what you need, sufficiently homogeneous and isotropic distribution of matter. So, and then we will try and find a solution. So this will be highly idealized, right? We don't live in a universe with an isotropic and homogeneous distribution of matter. But if you kind of zoom out enough, right, and coarse grain enough, then yeah, whether a star's there or over there, it doesn't really matter. If you average out on galactic length scales, then the matter should hopefully start to look fairly isotropic and homogeneous. So what we have to do is, well, to move forward, we have to give a definition of what we could mean by homogeneity and isotropy for a manifold, a spacetime manifold. So that's our first step, and where we commence discussion today is in just introducing a sufficiently rigorous and tractable definition of what might be meant by homogeneity and isotropy. So let's commence with the condition of homogeneity. What is meant by this? Well, physically, we don't occupy a privileged position in the universe. That's the assumption of homogeneity. And so that the universe should look the same no matter where we are. That's the assumption of homogeneity. And then the assumption, that's assumption 1. Assumption 2 of isotropy is that there's no preferred direction in space, time, space. There is a pretty preferred direction in the time direction, right? There's actually been numerous observations that support assumptions 1 and 2. They're obviously not true at the atomic level, but they're true at the galactic level to a fair degree of approximation. One of the most compelling observations concerning isotropy is that of the isotropy of the cosmic background radiation. And recently there's been some new dark matter distribution results that certainly go along with supporting the notion of isotropy. Isotropy of cosmic background radiation. So there's, some pretty compelling evidence that the universe should be pretty homogeneous and pretty isotropic. And what we want to do now is make a concrete mathematical definition that captures these notions, and then we want to exploit this definition and this to simplify Einstein's field equations to the point where we can find an analytic solution to them. So here we go now with the mathematically rigorous or precise definition that we're going to occupy ourselves with the next lectures. So a space-time manifold M is homogeneous if there exists a one-parameter foliation of M via hypersurfaces sigma t such that for each t and any points P and Q in this leaf of this foliation site sigma t, there exists an isometry of G of our metric which takes P to Q. And so you got to imagine, like, the universe is foliated in these in infinite number of these sheets that depend on a parameter t. And if you happen to find yourself on one of these sheets down here in the point P, then there always exists an isometry which takes, and that you have another point that you're interested in on this sheet sigma t, then there always exists an isometry that takes P to Q. Has to be an isometry, not a diffeomorphism. Now there's one remark worth making here. This is for homogeneity, no? Yeah. Now that's homogeneity. Now for isotropy, before we even start, we got to make a comment on how many observers will perceive the universe as being isotropic. Well, imagine the universe is sort of filled with an isotropic distribution of stress energy or matter and mass energy density. Then imagine there's at least one observer who can see the universe as isotropic. Well, the claim is there is actually no other observer that would perceive at that point. You fix a point and you take a look around and there's one observer. It's supposed there exists at least one observer that sees the universe as isotropic. Well, the claim is there can exist no other observer who sees the universe as isotropic at that point, because any boosted observer will see will, thanks to length contraction, perceive the background distribution of stress energy as being concentrated in the directions that are perpendicular to the motion of the observer. And so that's no longer isotropic. So there's only one observer at each point. Some boosted observers. See the background distorted. Okay, so that's just a comment before we get into the definition of isotropy. Whatever it is, whatever our definition will be, we have to admit that it won't apply to all observers, only one observer at any given point. So now we come to the definition of isotropy. So we say that a space-time M is spatially isotropic at each point if there exists a congruence of time-like curves and each of these time-like curves has a tangent vector UA, and these time-like curves must fill M, and they must have a further property that for all P in our space-time manifold and any two unit spatial tangent vectors, so these ones are space-like, we'll give them a name, S1A and S2A at the tangent space at the point P in our space-time manifold. So, you know, what we're thinking of here is we have an observer at a point P and you pick two directions pointing off into yonder and you look at space along those directions and you would say that space is isotropic if there exists a isometry of our metric, which leaves our observation point invariant and also the time-like vector, unit vector invariant. But it takes S1A to S2A. These two vectors are orthogonal to U. Okay. And so hopefully this is intuitively clear. If space-time is isotropic with respect to the correct observer at the point P, then no matter where you look, it's going to look exactly the same. And so if you pick any two vectors that point off in a space-like direction, then because it doesn't matter which way you look, you can rotate one to the other, and that would via an isometry, so you don't change the metric when you do that. So there's a further remark that one can make when you combine the conditions of homogeneity and isotropy. So for a homogeneous and isotropic space-time, the surfaces foliating space-time they must be everywhere orthogonal to these tangent vectors of the time-like vectors that are this congruence of time-like curves going through the manifold. And you can convince yourself why that must be the case. Because if there wasn't, for example, then there would exist a point P where you could pick a geometrically preferred spatial vector, and that would violate isotropy. So I just want to draw a picture before we finish for today that summarizes both isotropy and homogeneity into one picture. So here I've drawn the surfaces sigma t as foliating space-time, and then there's this congruence of time-like curves going through space-time, going through each of these leaves. And homogeneity is that result that says if you've got 2 points on the same leaf, the same site t, there exists an isometry of the metric which takes p to q. And if you're in one of these leaves and you have one space-like vector and another space-like vector that are both orthogonal to UA, then there exists an isometry which rotates S1A into S2A. So that's the notions of isotropy and homogeneity for a spacetime manifold. We're going to use these notions to highly simplify Einstein's field equations and then eventually solve Einstein's field equations in a highly restricted setting where these symmetries are present. But that's the goal for the next lecture. For today, we're now finished. Thank you very much and see you next time. Goodbye.